Good morning, good afternoon, good evening, wherever you are. Welcome to OpenEye Cadence Molecular Sciences Essentials in Computational Chemistry. My name's Paul Hawkins, and I will be your guide for this series. Today, part one, ligand-based lead discovery. So I have a couple of points before we get into the technicalities. If you would like, please let us know in the chat where you are signing in from. And if you have questions as I'm speaking, please add them to the Q&A section in the Excel events interface, and I will address as many questions as I can at the end of the presentation. So let's get going. Today and the entirety of the essentials will be of necessity a wide but shallow overview of the problems that we're looking at today. Again, ligand-based lead discovery. Lots of interesting things I don't have time to cover today. So there's a lot of additional material. We will be making a PDF available of the slides and the additional material. So if there are things you want to dig into more, please go and look at some of the extra reading and some of the resources in those hidden slides. So before I begin with the technical parts and the exploration of some of the science, I want to ground what we're doing in computational chemistry. And that's primarily supporting drug discovery. We're looking to get medication into the hands of patients who need it as efficiently and as cost effectively as possible. So I show here an outline of the process of drug discovery as a series of stages. As you can see simply by inspection, this is a very long process. 10 years, it's very expensive, well over $2.5 billion for the average drug, and it's extremely risky. 10,000 molecules going in to guarantee one drug emerging at the other end. I can't think of another business where you'd be in business if 99.99% of all your ideas fail. So this is a difficult process, and what we are doing in the essentials and what we do at OpenEye Cadence Molecular Sciences is looking at computational tools primarily to support the early stages, so the drug discovery stages, the first 4 parts of this process. Now, I'm going to use this neat workflow approach to illustrate where in the drug discovery process we are, but obviously anything involving science, particularly the science of human biology, is a lot more complicated than this. So thanks to Rob Mortimer-Smith at AstraZeneca for this idea. To get to the drug sometimes involves many more steps backward or sideways than it does forward. That's just the facts of human biology. Is very complicated. I will stick with the nice, neat process because it's a little easier to follow. So for today, the part of the process we're looking at is part 2, compound screening, where we're looking by some method or another to find patentable molecules that are going to effectively modulate our protein target and give a positive outcome on human biology. So this is discovering new lead compounds for the subsequent 2 stages. And if this stage works well, the subsequent 2 stages can be significantly accelerated. I show here a drug on the market and a clinical candidate. And in both cases, the initial lead here and here is essentially a substructure of the final drug or clinical candidate. So we can, by discovering good leads, make the second and third parts of the process much, much faster. So a good lead reduces time and reduces costs in the following stages. So doing good lead discovery makes a great deal of sense. Now, you might ask, why don't we just do this whole thing experimentally? So experimental screening of compounds, high throughput screening, HTS, is quite slow, unfortunately. To experimentally screen 1 million molecules will take weeks of time, and you'll probably have to wait months to get your particular set of experiments on the robotic platform. It's quite expensive, depending on the type of assay. You can easily spend $1 per well, so sometimes multiple wells per molecule, so well in excess of $1 million to screen 1 million molecules. And the success rates, depending on the target and the molecule database of screening, vary significantly. They can be as low as less than 1 in 100,000. They can be a lot higher. The median from recent literature seems to be somewhere around 1 in 1,000 or less. And that's why more or less everybody in this area has turned to the computational equivalent, virtual screening. A set of steps outlined on the left there for virtual screening as individual parts. I'd like to make the analogy between virtual screening and mining, and particularly gold mining. So this is the Kalgoorlie gold mine in Western Australia. And in this mine, you need to dig up about 3.5 or 4 million ounces of rock to get 1 ounce of 24-karat gold. So virtual screening is very similar. We have to look through a lot of compounds to come up with very few that are going to be interesting. To do that, there are a lot of separate parts, and I'm going to cover many of these parts today, looking at preparation of databases and then three-dimensional and two-dimensional ligand similarity methods. The docking part is coming in Essentials number 2, so please join me for that. So the first part of the virtual screening process is, if you will, to define your mine, to define the space of molecules that you'd like to search in. And I'm going to use two types of molecule collection here, somehow pre-generated or customized. So firstly, pre-generated. I'm going to divide these also into two parts. Annotated collections, where there's at least one piece of biological data for every molecule in the database. And the grandfather of this is certainly PubChem, with about 120 million molecules with data points added. These collections have some significant advantages. You can generate knowledge-based targeted subsets, all molecules active against a kinase or a protease or a GPCR. These libraries, as you'll see, are relatively small, only 100 or so million molecules, much smaller than some other available collections. Disadvantages for these sets include there's no necessary path to obtaining the molecule. There isn't necessarily a vendor who will provide you the molecule. It may have to be synthesized, so there's a lot of at-risk chemistry. And there's no inherent novelty in any of the molecules in these databases. They're all available for search to anybody who wants to search them. The novelty, the intellectual property, only comes with the application of the molecule to your target. The second kind of pre-generated collection, what I call unannotated. Here, there's simply a definition of the molecular structure and a molecular identification of some kind. These are the sorts of databases generated by vendors who I'm sure you're mostly familiar with: Enamine, Wuxi, Liverpool Chirochem, Otava, etc. So these databases are much larger, as you can see, into the billions or tens of billions and up, as I'll show in a moment. So these libraries, the size is both an advantage and a disadvantage, as you'll see in a second. The vendor model is very simple. You exchange money for molecules. So no at-risk chemistry, and the vendors have become very good at predicting success rates and delivery time, so you can stay on a predictable schedule. However, a disadvantage shared with the annotated collection is that there's no inherent novelty in the structure. For the most part, everybody has access to the same molecules, and they can all be searched by anyone who wants to search them. So sticking with these unannotated vendor collections, these spaces here in blue are the commercial libraries, are enormous. If you look again at the axes here, these are the increments in orders of 10. The largest libraries from vendors are well over 10 billion, and some are getting into the trillion range. So commercially accessible molecule space is extremely large, and as I'll show in a moment, self-generated spaces can be even bigger. So a lot of focus I'm going to get on today is about how to deal with large libraries efficiently. So the alternative to a pre-generated collection by someone else is to generate your own customized collection. And there are various ways of doing this, and I'll go through each one briefly. The simplest way is traditional combinatorial chemistry, initially at a single site. We'll start a molecule here. These are binders for a kinase called TYK2. We like to elaborate, for example, the amide portion. So we'll do the amide disconnection, reveal the aniline starting material, and then provide a set of reagents, carboxylic acids, acid chlorides, anhydrides, etc., to do this amide coupling and generate a library of molecules substituted at the same position as amides. This has the advantage there's well-defined chemistry that you can predict fairly well how it's going to work, and you're going to generate a relatively small library, though of course, if you have 3 substitution points and 1,000 reagents at each point, that's already 1 billion molecules. Because you're defining a reaction at a single position in a single piece of chemistry, you've got limited diversity and probably therefore limited structural novelty. So moving up a range in scale, we could take the same molecule, identify the same disconnection, but now think about other kinds of chemistry that could be done at that same position. So along with amide coupling, we may have arylation or alkylation chemistry, and so on. Find reagents to match that chemistry, and now we can generate lists that contain arylation chemistry and amide formation and alkylation, and so on. So these libraries, as you can imagine, can get very large. They can be quite structurally diverse, and the chemistry is known. But the synthetic difficulty can be challenging, especially if you're looking to do incompatible or difficult chemistry at multiple sites in the same molecule. Going a step down in size, we could ask a slightly more general question, where we say, well, there's a part of the molecule whose structure I want to manipulate to change overall molecular properties. So I might say I'd like to change something about the 2,6-dichlorophenol group. So there I'm going to do substitutions at various points. So meta here, and para here, substitutions, for example, manipulating, for example, solubility, or substitutions manipulating log P in a relatively predictable fashion. So these are precedented transformations, particularly in the matched molecular pair, or MMP concept. There are relatively few transformations that have predictable changes in property, so you're getting limited structural diversity, and there's no inherent path to synthesis here. We're simply adding fragments to a molecule to move properties in a fixed direction. Now we can take another approach and be much more agnostic about the chemistry we'd like to do. So again, starting with the same molecule, we could automatically or manually identify chemistry that we could do, and then identify reagents that could be compatible with all those kinds of chemistry. So again, we have an amine equivalent, perhaps a carbonyl equivalent, or an aldehyde equivalent, or an aryl equivalent. And again, at the biphenyl bond, we have aromatic or vinyl equivalents, generating large numbers of possible synthons, which we could again search for in a building block database. Now we can enumerate extremely large libraries that are very, very diverse, where they bear quite a limited relationship to the structure of the original molecule. So this can rapidly produce enormous chemical spaces, which is both an advantage and a disadvantage. You're getting lots of diversity and novelty at possibly a cost of high synthetic difficulty. So many different approaches across a wide range of scales, many of which can rapidly produce multi-billion, trillion member libraries. So why the focus on these much larger libraries? Well, I'm going to show you some results from some ligand-based searching, that I think things apply across the board. That results here from AstraZeneca, working on actually one of our tools from OpenEye, a 3D similarity tool called FastRox. On the left here, we have the score, a three-dimensional similarity score, which I'll talk a little bit more about later. And here we're looking at the scores for top-ranked molecules in databases of increasing size from 100,000 all the way across on the right to 10 billion. So we'll see these larger libraries contain better matching, better scoring molecules. On the right, we see the structural diversity, the number of unique scaffolds in the top-ranked hits. And again, the number of unique scaffolds increases linearly, monotonically, with all of the increases in library size. So we're getting both more diverse and better scoring hits. The downside, of course, is your calculation time will scale linearly, more or less, with the number of molecules in the database you search. So a lot of focus in virtual screening, particularly for ligand-based, is in these large libraries. More of that in the last half of the talk. Now, no matter where you get your molecules from, generate them yourselves or get them from vendors, it's unfortunately true that probably the molecules you get are not necessarily going to be quite ready for you to do virtual screening on directly. They'll need to be processed. Something that was quite common in the early days of vendor libraries was chemical representation problems like this, a neutral 5-valent nitrogen, chemically impossible. So molecules like that would need to be removed. We then need to think about something a little more subtle, application of tautomer state, for example, should we have one or multiple? And then, of course, protonation state, should we have one or multiple? And it might seem, well, let's just have them all. But for some molecules, a single molecule can have a large number of alternate tautomer and protonation states. So this molecule, for example, is one. Here's an alternate protonation state, an altered tautomer, another altered protonation state. There are at least 32 variants for this single molecule. So imagine if you have many molecules in your database of this kind of structure, you're going to get a very large expansion in your database. So you're more likely to get whatever the relevant form is. So you're going to increase your signal, but at the cost of a lot of extra noise, many inappropriate or not relevant tautomers or protonation states. So the enumeration problem needs to be thought about carefully, again, especially for large libraries, as it can massively expand the size of your collection. So then we've defined the mine, we've decided which chemical space we'd like to search in, and the next thing to do is sort of remove the molecules we know we don't want to process. So lots of different approaches to this. At the very simplest representation of molecular structure here, from a string like this, SMILE string, we can read off properties like the number of stereocenters, number of heavy atoms, donors, acceptors, things like that. So these very simple properties have been used for a long time to attempt to describe the sort of drug-likeness of a molecule. The most famous of these heuristics is developed by Chris Lipinski when he was at Pfizer, the Lipinski Rule of Five, or ROF, and the rules are here. Now, this was a very, very popular approach. Almost straight away it was published. It's appealing because it's a pretty fast way to filter out molecules that seem unlikely to be successful. Unfortunately, the rules have been misapplied almost as often as they've been correctly applied. And while this is a very powerful approach, especially when you combine multiple different filters together, the filters that you're using, the properties you're applying, are extremely crude, and they may not actually represent what defines drug-like space, particularly in terms of key properties like solubility and membrane permeability. And I'll come back to that in just a second. So we can use these 1D methods, and they can be powerful if used in a thoughtful way. The next up is to think about the molecule as a fully connected molecular graph, where the nodes are the atoms and the edges are the bonds. And in this sort of representation, we can do substructure searching. So here, most of this is applied to remove substructures that we don't want in the molecules in our database. And I'll take one particular example: structures that impart toxic properties to the molecule in the body. These have been known for quite a long time. These have been increasingly uncommon, particularly in vendor databases, as the vendors have become more intelligent about removing possibly difficult functionality like this. The opposite side, of course, is there may be substructures you do want, and I'll pick on one in particular. This is a kinase binder. This is the hinge region up in the top right here, and you have the standard sort of canonical donor acceptor motif separated by one or perhaps two heavy atoms. So this would be what we call a privileged substructure, and you might want to keep deliberately molecules that have substructures like this because you know they're going to be effective binders. So for the most part, however, filtering is about what I call negative design, to design your space away from molecules you know you don't want. So you're trying to reduce the space of these very large libraries by removing the molecules you do want, so that you can focus on the molecules that are going to be helpful. Now, I would warn here, there's some very interesting work published in the last few years from Novartis, showing that unfortunately a lot of one-dimensional property filters don't really address the problem at hand, and they aren't very effective for focusing into permeable and soluble molecule space. So the 1D properties can be important, but again, apply with care. So negative design, these filtering approaches, essentially are thinking about scoring molecules in a binary way: yes, no, in, out, 0, 1. So now what I'm going to do is use 2- and 3-dimensional similarity calculations to actually perform the virtual screening, to score and rank an entire database of molecules, to put the interesting molecules at the top. So in the ligand-based world, this is a very, very simple approach. We decide the mine, the database, we get rid of the rubbish, we decide our query molecule, and we do our virtual screening. And then after that, of course, success, where success would normally be you found a set of active molecules. Lots of different approaches to this. Today, again, we're looking at ligand-based lead discovery. I will follow up in Essentials Part 2 on structure-based, but for today, again, looking at 2D and 3D similarity methods. And we can think about success or performance in these methods on 3 axes. First, speed. Obviously, these very large databases can be computationally demanding, so high-speed methods are helpful. And 2-dimensional methods, as you'll see, are obviously by far the fastest. Another axis of performance here on the z-axis is accuracy. Given the list of predicted active molecules, we'd like to have the highest proportion of genuinely active molecules in that list as possible. And then a third and very important axis is structural novelty. As I'll get into later, 2-dimensional methods tend not to give highly structurally novel molecules, 3-dimensional methods more, and as we'll see in Part 2, structure-based methods give even more structural diversity in the hits. So two-dimensional virtual screening, again, relying on this graph-based representation of the molecule. I'm going to represent molecular structure in this approach using something called a fingerprint, which I'll get to in a minute. But ligand-based virtual screening in 2D or 3D depends entirely on the truth of the similarity principle, which is written down here. So in order to utilize the similarity principle, we have to represent molecular structure in an appropriate way and then calculate molecular similarity in a way that's relevant to its biology. So fairly simple things. And by far the most common way of representing molecules for virtual screening in 2D is using something called the molecular fingerprint. So the fingerprint's a very simple idea. It's a string or a vector of bits where each bit tells you about some piece of the molecule being present or a functionality being absent. So for example, here we have a molecule that may have aromatic rings, nitrogens or oxygens, and that information is embedded in some form into that string, the fingerprint. There are basically two types: binary fingerprints, where the feature is either there or not, or count fingerprints, where we count the number of times a feature is present. So 2 nitrogens, 2 oxygens, 0 chlorines for the count fingerprint. From the rest of this, I'll talk about binary fingerprints, but everything I say applies also to count fingerprints. Lots of different types of fingerprint. I'll divide them into 3 broad classes: substructure type keys, including probably the first molecular fingerprint used, and that's the max key; topological fingerprints, where we look at 3 atom groups or 4 atom groups. These are often called torsion fingerprints; pharmacophore fingerprints, where we'll have 2 pharmacophore features, acceptor and a donor, separated by a certain number of atoms. And then we have the fairly common and quite widely used hash fingerprints, including one of the most popular in this area, the circular or the Morgan fingerprint. So diagrammatically, a max key asks the question, do we have a certain functional group? In bit 1, do we have a phenol group? Yes. Do we have a chlorine? No. Do we have a fluorine? No. Do we have a bromine? No. Do we have a primary nitrogen? Yes. And so we build up the fingerprint that way. The others, the topological fingerprints and the hashed fingerprints, are hashed from a large fingerprint. They're reduced down to a fixed size. Tree fingerprints or path fingerprints look for different paths through the graph of the molecule and fill up the fingerprint according to whether a particular path is present. Circular fingerprints take substructures or fragments of the molecule centered on a particular heavy atom and going out 1 or 2 or 3 bonds and generating increasingly large substructures of the whole molecule. And again, these are extremely popular in ligand-based virtual screening at the 2D level. So now we have a molecular representation, the fingerprint. Now we have to compute similarity. Lots of different ways to do that. So 2 basic classes: symmetric measures, and by far the most famous symmetric measure is the Tanimoto. The O term here is the overlap between 2 molecules, F and G. In this case, it's the number of bits in the fingerprint that are on in both. I and F and I and G are the individual number of bits on in 2 separate molecules, and again, that's the overlap. By construction, this is bounded 0 to 1. 0, no bits in common between the 2, absolute difference. 1, all bits in common. The molecules are essentially the same as far as the fingerprint is concerned. We have, of course, asymmetric measures, and the most famous of these is the Tversky measure, very similar in construction to Tanimoto, except with the introduction of this weighting parameter alpha, which weights similarity toward either the query molecule or the database molecule. If alpha equals 0.5 here, this actually reduces to a symmetric coefficient, which is known as the dice coefficient. So we have a representation method, we have methods of similarity. So let's go and do some searching. So here's a quick illustration, I hope, of why we find 2D methods to be particularly useful. Sorry, a visual problem here. Never mind. What I was going to show you here is very fast 2D searching. We can achieve rates here of over 100 million molecules a CPU second, and some are almost an order of magnitude faster than that. A downside of 2-dimensional methods is they tend to give you molecules that look rather similar to the structure of your query, so you're not finding new property space, particularly not finding new intellectual property space. So 2D is very fast, but isn't always very effective for finding new intellectual property, new areas of structure space. So I'm going to move up from 2D to 3D and look at 3-dimensional properties such as shape, electrostatics, and pharmacophores. So here we're looking at the molecule as a 3 the entity Cartesian positions of the atoms in space. So to do that, we're going to need to put the molecular structure in 3D. So we're going to need to generate molecular conformations. Then we're going to do the searching, and of course, then we're going to end up with success. So pre-step for all 3D methods, of course, is generation of the conformations. So this is essentially a two-part process. The first part is sampling. And there's lots of different algorithms here. I'll briefly touch on a few of these later on. And then once we've done sampling, we have to score each of the conformations in some way that tells us about its relevance or its stability. And in the great majority of cases, we'd use some estimation of molecular energy or strain energy. We can also use sort of the converse of energy, which is probability. High energy, low probability, high probability, low energy. No matter how we do the sampling and the scoring, the goal is always the same, to generate a small ensemble of relevant conformations. Small because the calculation time downstream depends entirely on the number of conformations coming in, and relevant in that we'd like to make sure we're sampling at least some of the time space around the biologically relevant, the bioactive conformation for each molecule in the database. So sampling methods I'm going to split into basically two parts, stochastic methods and deterministic methods. Stochastic methods are going to give you a different outcome with identical inputs, and deterministic methods aim to give an identical output with identical inputs. So if I put that on a scale, fully stochastic methods include Monte Carlo, MC, genetic algorithm, GA, and distance geometry, DG. Fully deterministic methods, rule-based approaches, which usually involve something called torsion driving. And then I'll put molecular dynamics in the middle. Newton's laws of motion are not stochastic, but a combination of floating point precision during calculations and somewhat chaotic nature of input means molecular dynamics calculations don't always give you exactly the same output for the same input. So I'm going to put them a little in the middle. So lots of sampling methods. We now, of course, need to score the conformations. And again, by far, the most common approach here is to use a force field using a classical mechanics approach. We can go up in levels of theory to semi-empirical or even to full-scale ab initio. But as you'll see in a moment, these electronic structure calculations are enormously slower and scale rather worse than force fields. The converse, again, is probability. And here we'd be looking particularly at the probability of finding a particular torsion in a molecule by comparing the frequency of a particular torsion angle in solid-state databases such as the CSD to the torsion in the molecule. The more frequently a torsion occurs, the more likely it is that conformation is to exist, whereas the less frequently a torsion is found experimentally, the less likely we believe that torsion is to be existing in a real conformation. But again, most approaches here are focusing on force fields for energy. Here we have time on our x-axis and some estimation of accuracy down y. Force fields, the fastest but arguably the least accurate. Semi-empirical methods and ab initio going to down and to the right. The n here number is how these techniques scale with the number of atoms in the molecule. And as you can see, these high levels of theory, NP2 or even coupled cluster, are scaling very badly with the number of atoms in the molecule, n to the 5, n to the 6, and n to the 7. So these are really out of reach for processing even more than a very small number of molecules. So for the most part, we're going to focus on conformation sampling and scoring using force fields. So to put the sampling methods on some sort of time scale here, by far the fastest methods are torsion driving, down in the tens of milliseconds per molecule, all the way up to molecular dynamics, which is tens of thousands of seconds per molecule. So I'm going to briefly compare two methods of conformation sampling for various different properties: a stochastic method, distance geometry, and a deterministic method, torsion driving. And I'm going to look at these three for three different sort of properties: accuracy of reproduction of structures from the solid state, the number of conformations in the ensemble with certain properties, and the speed with which that ensemble is generated. And what we'd like is to have low deviation from the experimental answer, a small ensemble, and a high speed. So comparing torsion driving on the left, distance geometry on the right, these two approaches are almost equivalent in accuracy. The stochastic approach, distance geometry, on the left, produces a rather smaller number of conformers than torsion driving. But as I mentioned, torsion driving approaches can be much faster for this particular data set. the times here are down in about the 30 millisecond at a median, whereas the distance geometry approach is about 100 times, about 2 orders of magnitude slower. So depending on your particular requirements, one or other method here may be better for your particular project, your particular problem. I just like to say that I'm talking about pre-generated conformations. One, of course, can do conformation generation on the fly. Of course, this is going to be slower and also repetitive. Pre-generation of conformations can be a lot faster, and you can then spread the cost of pre-generation over all subsequent calculations on that pre-generated database. So for very high speed, pre-generated databases really are a must. Okay, so now we're ready to actually do some 3D virtual screening. We can start to look at shape, electrostatics, and pharmacophores. But before I do that, I'd like to take a short break from the plots and the charts and the science and talk a little bit about art, and particularly early 20th century Belgian surrealism. And this early 20th century Belgian surrealist, his name was René Magritte. And this is one of Magritte's most famous paintings. It's called The Treachery of Images, and the text in the painting reads, "Ceci n'est pas une pipe," or "This is not a pipe." And indeed, Magritte is correct. That isn't a pipe, it's just a painting of a pipe. And in the same way that that's just a painting of a pipe, that is not a molecule, it's just a picture of a molecule. We use it all the time. It's the basis for all the 2D methods I spoke about a moment ago, but it is just a picture. And you might say, well, a 3D thing, that's an actual molecule. I would say, well, no, that's a set of atoms joined together by bonds. That's not a molecule. So, of course, it's a molecule. I would say, well, quantum mechanics people tell us there are no such thing as bonds. There are only nuclei and electrons. What do quantum mechanics people know? More importantly, scientific studies show that proteins, receptors, give no rats. They don't care at all about atoms and bonds. What they care about are shape and chemical features. They want to bind molecules that are complementary in shape to their binding site, and the protein wants to bind molecules that have complementary features, a donor on the protein, an acceptor on the ligand, making complementary features. So for this section, I'm going to think about molecules a lot as a shape with a set of attached or embedded chemical features, or what we here at OpenEye would call color. And these are the usual kinds of things you think about: donors and acceptors, anions, cations, etc. So we can use this representation to compute molecular similarity in 3D. So here's a molecule I showed you earlier. This is actually a CDK2 binder for a kinase involved in a number of human cancers. This is another molecule that also binds to CDK2, rather different chemical structure, more of which in a moment. Here are their three-dimensional conformations directly out of the co-crystal structure from the PDB. Here are these molecules as a shape with attached chemical features, and I've added the graph here for clarity so you can see where the features come from. And we can now align and score these two molecules based on their shape and chemical feature or color similarities to get both an alignment and a similarity score. We happen to use what's known as Gaussian functions here for a continuous scoring method. I'll come back to that in a moment, but that's an implementation detail that allows us to get continuous scores, and the scores we get out of this are exactly the same scores that we get for 2D fingerprint comparison, metrics like the Tanimoto and the Tversky similarity measure. So, well, that's great. Why are we thinking about 3D? This all sounds a bit complicated, shapes and Gaussians and so on. 3D, I think, has an advantage over 2D that I think this example will make obvious. Two molecules here, very different in 2D structure, very similar in biology. They're both equipotent and reasonably good binders for the CDK2 protein. So they're highly similar in biology, but very different in 2D. If we compute the fingerprint similarity between these two molecules using a path fingerprint, it's 0.12 on a scale of 0 to 1. If we compute the shape Tanimoto between these two molecules, it's 0.8 on a scale of 0 to 1. So they're much more similar in shape than they are in 2D. So in this anecdote, we're seeing the alignment of these two molecules reflecting a high similarity in shape that reflects the high similarity in biology. So the similarity in biology is detected with the 3D approach, but not detected with 2D. And you might say, well, okay, 0.8 is bigger than 0.12, but I don't know how either of these scores distribute. So is 0.12 actually quite a good fingerprint score? So Fair question. Luckily, I have an answer. So here is the distribution of path fingerprint Tanimotos for 10 million randomly chosen pairs of molecules out of a database of drug-like molecules. And here, a score of 0.12 is about the 80th percentile or so. So over 20% of all randomly chosen molecules have a path fingerprint similarity greater than 0.12. So this is not an interestingly high score. So these are not similar in fingerprint space. The distribution of shaped Tanimoto for the same number of pairs out of the same database of molecules is much more normal, has a mean of about 0.5, standard deviation of around 0.05. And so here, a shaped Tanimoto of 0.8, only about 0.1%, one molecule in 1,000 chosen at random, has a similarity that or higher. So a shaped Tanimoto of 0.8 is a very significant similarity, and it's telling you something interesting about the nature of the two molecules with that similarity. So now I'm going to look at using 3D and a little bit of 2D for virtual screening success. So a short note on how I'm going to measure virtual screening success with these different methods. I'm going to use something called the ROC plot, which plots on X the false positive rate. So this will be finding inactive molecules in virtual screening. And then on Y, the true positive rate, which in virtual screening is finding active molecules. We can use this curve in two ways. I'm going to focus on one of them, which is to look at the area under the entire curve. One may also look at areas under parts of the curve to get early recovery measures. The area under the curve for the ROC plot can measure something called discrimination, which says if you choose an active molecule and an inactive molecule at random, what's the probability that the active molecule gets a better score? And so perfect performance measured by the AUC is 0.5, which means there's a 50-50 chance that an active molecule is scored better than an inactive, and perfect is 1, which means there's a 100% chance that an active molecule is scored better than an inactive molecule. Lots more details in the supplementary information, including how to compute errors and estimate uncertainty in these kinds of methods. So let's do a little bit of virtual screening comparison. On the left here, I'm using heavy atom count to rank the molecules, so something that shouldn't work for virtual screening. In the middle, I'm using a fingerprint, using a Tanimoto similarity, and on the right, I'm using shape and color from our tool ROC's, rapid overlay of chemical structures. AUC here, red line is 0.5, random, 1 is perfect, and you can see by eye and numerically that ROC's here shows a small but significant advantage over the fingerprint approach. This is a statistically significant difference. And if you're interested to understand a little bit more about what confidence intervals are for and how we can use statistical testing to compare results for methods and make confident predictions about future performance, please join me for Essentials Part 4, where I'll be looking at decision-making in computational chemistry. So returning to our virtual screening problem, looking at 2D and 3D methods. If I plot a 2D similarity, fingerprint Tanimoto here on X, and then on Y, the ROC similarity, this is a sum of 2 Tanimoto coefficients, 1 for shape and 1 for color, so it scales 0 to 2. You can see that the fingerprint similarity and the ROC similarities do not relate to one another. They don't correlate. So they're seeing different similarities between molecules. Happen to be here using a molecule I used a moment ago. This is imatinib, Gleevec, a well-known anti-cancer compound. So this lack of correlation between 2D and 3D is quite interesting, and I'll come back right at the end of the talk to how we can exploit that to improve virtual screening performance. Now, another very popular approach to comparing molecules in 3D using either features or features and shape is the pharmacophore approach. The definition is written here. The features are the same I was talking about with the ROC's tool and color, same features. In pharmacophore tools, some tools use shape plus color, some use color only. So in the pharmacophore approach, we put a pharmacophore point with a particular radius on it and a distance between them. And then molecules will be aligned by matching triangles of features together, very well-established piece of technology. In pharmacophores, scoring has a little bit of a binary element in that most molecules won't match the pharmacophore and therefore don't get a score. So only a small fraction of the database will get scored, whereas in continuous scoring methods, the ROC's tool I showed you earlier, every single molecule in the database gets some kind of score. So 2 different approaches to scoring and 2 different ways of using scoring. Pharmacophores use them partly as a classifier. Now, whether we use shape and color, shape and pharmacophore features, we are defining the features here in a quite simple way. We're using graph-based matching here. NH is a donor, double bond oxygen is an acceptor, and so on. We can raise the level of physics by abandoning that sort of graph-based 2D approach to identify features and use a full electrostatic potential representation. Lots of different ways to do that. We can look at extrema of the electrostatic field. We can look at the electrostatic field in sampled points around a particular molecule. And we can look at the entire full electrostatic potential. In either case, we compute the electrostatic potentials for the query, and for each of the database molecules, we compare them and generate a similarity in electrostatic space versus color space. Without going too much into the details, the general outcome for this is, because you're not using graph-based matching to assign features, you get higher structural diversity from electrostatics calculations, but they're substantially slower than the feature batching approaches, the pharmacophore type approaches, because we're using a lot more physics, which involves a lot more compute. The differences can be as low as a 2-fold or so to up to over 100-fold different. But this is an appealing method. So see here, I'm plotting similarities in sort of the pharmacophore shape and color world here on X versus shape and electrostatics on Y. Pleasingly, they're not uncorrelated, but they're not strongly correlated either. So again, electrostatics and pharmacophore or color features are looking at molecular similarity in different ways. So why would we use 3D? Well, 3D is a really interesting approach because it allows us to look at rather higher levels of structural diversity. So what I'm going to show you here, sort of live, is searching, again, using our query from the 2D search, GleVec. And I'm going to use that to search a 3-dimensional database of molecules from the enamine diverse collection, and that is around 90 million molecules or so. So the 3D conformation for the GleVec molecule has been generated in the background, and we're doing a 3D similarity search using our GPU-enabled implementation of shape and color, which we call FastRox, and this runs somewhere on the high side of 1 million molecules a GPU second. Compare that to CPU speeds of between 1 to 100 molecules or so CPU second. So here are the results back. There's GleVec, and here are our 4 top-ranked hits. And simply by eye, you can see that these 4 hits are quite different to one another, and they're quite different to the GleVec query. So if we look at that in a teeny bit more detail, again, here's GleVec. Here are 6 of our top-ranked hits, very, very dissimilar to one another. Lots of different areas of chemical space, possibly new areas of intellectual property space. And again, not only do we get these interesting graph-diverse hits, we can also look at the alignments between the query, which is in green, and the individual database molecules. So 2D v 3D. We get, as it showed, I hope, good virtual screening performance out of 3D, though the comparison's difficult, and I strongly recommend you read this paper from A.J. Jain on what he calls the inductive bias in medicinal chemistry. Well worth thinking about. As I just showed you, we're expecting high chemical diversity out of 3-dimensional methods because they're not tied strongly to the details of the molecular graph, and that's particularly useful for understanding and finding new areas of intellectual property, of patentable space. And as I just mentioned, one thing that we do get out of 3D methods you can't easily get from 2D is an alignment between different 3-dimensional structures. So again, here are our CDK2 structures. So what we can use this for is to start to enable the AI between our ears and to understand how one set of features in one molecule transfers to another one. So we can use knowledge from one chemical series to accelerate progress with a second chemical series based on understanding how their features match or don't match in 3D space. We can also use the overlay in a less guided way to think, again, AI between our ears, about constructing new molecules without reference to the graphs, the 2D structure of all the molecules we already know. So generate new design hypotheses from these 3D overlays. So we get a lot of diversity and highly informative alignments, but we pay a substantial cost. These 3D methods are several orders of magnitude slower than 2D, so need to be carefully thought about to be scaling into the multi-billion range. And for speed at that sort of scale, you do need to pre-generate and store your 3D conformations with the attendant costs in time and money. Okay, so we've defined our mine, decided which database we'd like to search. We've filtered away the molecules we don't want with 1D or 2D filtering methods, And then we've done our virtual screening with 2D or 3D approaches. The next step is where the value comes in some sense, and that's to triage that hit list, looking for the most interesting, the most valuable molecules. So several things I'd suggest you think about when you've got your hit list. The first is to look for maximum information per molecule. Try to find the structurally diverse molecules, and you can find them, again, by clustering, for example, and they're structurally diverse at the 2D level or structurally diverse at 3D. So we can cluster using things like fingerprints. We can also cluster using similarity at the shape level. Look for the molecules that are most interesting. You'll always get top scoring molecules by definition, but are the top scoring molecules unusually high scoring in the context of your particular calculation? So what you're looking for is there's going to be a background distribution of inactive and uninteresting molecules here in blue, and then a small distribution of molecules that have a different mean standard deviation, and this is, you hope, where your active molecules are. And so defining this separation between them can help get much more interesting molecules with much more confidence that they're actually worthwhile. And that confidence is important because you're going to put a lot of at-risk effort into the molecules you pick. You're going to need to purchase them, synthesize them, and then assay them. So there's a lot of experimental cost and time at risk. And so you want to be confident. So you can, if you want, attempt to determine for each database and each protein target which method appears to be best using retrospective experiments with suitable data sets. But that's very time consuming. Assembling the relevant data is sometimes very hard. A much more efficient approach is to use a consensus of different and reliable methods. And I point you to a couple of interesting papers recently, one on using consensus or data fusion with fingerprints, the other combining fingerprint and 3D methods. Again, recall that I showed fingerprint similarity and 3D similarities are very different, so it only makes sense to use them together. When you do, you can get quite significant improvements in performance. So here I'm going to show you a performance again of our 3D tool ROX on its own on the left. Again, higher here is better. In the middle and the right, we have two different ways of fusing similarities from 2D fingerprints with the similarities from 3D from ROX. And as you'll see, we get a substantial increase in the virtual screening performance, and that's a strongly statistically significant difference. Again, I'd like to have a look into more of this. Please join me for part 4. So consensus scoring methods make a lot of sense, particularly if you have a 2D method which is going to add no compute time because it's so much faster than any of the alternatives. So to circle back to the beginning and think about the comparison between computation and experiment. These ligand-based methods are extremely fast. We can screen billions of molecules in a few seconds, even on CPUs with some modern fingerprint methods. And even 3D methods, our FastRox GPU approach, we can screen 1 billion molecules in about 20 minutes. These have therefore very low compute costs. Compute costs for 1 billion molecules at 2Ds in the cents range, and it's in the $20 to $25 range per billion for 3D. And with appropriate care, virtual screening can actually return much higher hit rates than experimentation. Certainly hit rates have been reported lately well in excess of 1 in 100, so orders of magnitude higher than we're obtaining from experiment. So all very good news. The last stage on our journey from the mine to the gold is actually selecting the molecules that you're really going to test, synthesize, purchase. That's the bit that separates good virtual screening from great. That's the part where the human expertise comes in. And that's the part, unfortunately, computation has limited help with. So this is the bit that really requires expertise and care from the user. So with that, we've come to the end of the journey. We're at the end of the funnel. We've got the gold in our hands. So again, to remind you, lots of things I haven't had time to talk about today. Lots of material in the supplementary information. So please, when that's available, go download the PDF, dig into some areas of interest. If you'd like to follow along with the rest of the journey, we have planned 3 more parts. The next on structure-based design, the 3rd on binding free energy prediction, and the 4th on decision-making in CompCam. So I will just leave you with some follow-up. If you're interested in looking at some of the tools that we provide in this area, please be in touch. If you're in academia, we make access to our entire suite available for free. And the recordings will be available till the end of the year. Please see some more information in emails. In the meantime, thanks very much for coming along, staying with me, and I look forward to seeing you at the next one. Goodbye for now.